So it has been almost 60 years since the advent of the flame ionization detector, or the FID. The FID holds the crown as the most widely used detector for gas chromatography because of its high accuracy, robustness, and its ease of use. But it has its limitations. And those include the inability to detect certain carbon compounds such as carbon monoxide, carbon dioxide, formic acid, formaldehyde, other aldehydes, and organic acids. And it also has a different sensitivity to different compounds because of the different carbon environments of those compounds. But today I'm excited to tell you about a brand new technology that is revolutionizing the way we detect carbon compounds in gas chromatography. Now, the motivation for this technology begins back when I was a graduate student at the University of California, Berkeley, and I was looking at methanol dehydration to dimethyl ether on solid acid catalysts. Now, in order to measure the kinetics of this methanol dehydration to dimethyl ether, which I'm showing here is the turnover rate as a function of the methanol pressure, I had to be able to accurately measure the concentrations of methanol and dimethyl ether. Now, as a scientist, it doesn't get any better than this. The reaction was selective to dimethyl ether, so I only had 2 peaks in my chromatograms and thus only 1 response factor to calibrate for. That was pretty nice. Then, like a naive scientist, I raised the temperature and I started to make hydrocarbons, oxygenates, and gasoline-like molecules. Indeed, these are the conditions that are typical for methanol to gasoline, methanol to hydrocarbons, methanol to olefins. And now I was in over my head. I had chromatograms that had hundreds of peaks. Many of those peaks were not identifiable, even with mass spec. The compounds were very hard to calibrate for. I either had to synthesize my own compounds or purchase them for expensive prices and handle them, and they might have been degrading as I was doing that. So, like any smart graduate student, I lowered the temperature back down to 433 Kelvin. I wrote a few papers, I got my PhD, and I got out of there. So this data is actually from a much smarter and a much more ambitious graduate student who took over my work where I left off, Michelle Sarrazin and the Iglesias group at UC Berkeley. But this problem continued to haunt me ever since I left, so I wanted to figure out a way, is there some way to quantify all of these peaks? We actually knew this was a boiling point column, so we knew generally where compounds were coming out. We could inject them in a mass spec and get mass fragmentation patterns, but we couldn't quantify them without buying these standards or synthesizing them, and this was a real issue. So was there a way to do this? Well, to understand why we calibrate and whether there's a way to eliminate calibrations of the FID, we need to go back and look at the flame ionization detector and understand why it has this different sensitivity to different compounds. So the flame ionization detector, as its descriptive name alludes to, is really just a flame with hydrogen and oxygen. And it burns compounds, carbon compounds, as they come through the flame, and it creates these carbon cations. And these cations are counted, or the electrons that are balancing them are counted with an ammeter in your GC. Now for straight chain alkanes, the sensitivity or the number of carbon cations that are formed are about 1 in every carbon atom you form, 1 in every, million carbons you form a carbon cation. And that sensitivity is roughly the same for methane all the way up to C30s. There might be differences of about 10 to 20%. But when you add an alcohol group or an acid group, that sensitivity can go down 5-fold or hundreds-fold, where you don't even see that in the FID anymore. And this is because these alcohol groups or these functional groups change the propensity in this flame to form those carbon cations. But we can ask ourselves, what if we had some magical catalytic device where any molecule that went into it came out as the same molecule, or an ensemble of methanes in this case, and then we were just detecting methane in the flame ionization detector? Then the response of all these molecules would actually just be the same on a per carbon basis, because we're only measuring methane by the time it gets to the FID. So I'm excited to tell you that the Activated Research Company, for the first time, has commercialized a device, a reactor here, to convert the column effluent of any GC into methane for uniform detection with the FID. So now if we go back to the methanol to gasoline chemistry that haunted me while I was a graduate student, we can ask ourselves what happens to this chromatogram when we react everything in here to methane. So this blue line, which might be hard for some of you in the back to see, shows the new FID signal now that everything has been converted to methane. So now the signal here is directly proportional to the carbon content of each compound. So now instead of calibrating each peak for the individual type of molecule, now all we need to do is integrate the peaks. And that gives us the relative carbon amounts of each of these different components. We could also group these peaks into C4, C5, C6 lumps and get an entire concentration of that lump just by integrating that, co-eluting peaks and all. So we can also look at some peaks down here early on which weren't apparent at all with the FID only signal. And if we look closely at that, what we see on this 1% phenyl column is CO, CO2, and formaldehyde, a large amount of formaldehyde that we didn't see at all with just an FID. And this was actually very important for Michel Sarazin's research in elucidating the mechanisms for this MTG chemistry and the fundamental bond-making chemistries, the CC bond chemistries, that happen on these solid acid catalysts. So you may be asking, this is great, how can it help me with my analysis, and where is the proof that the quantification is actually accurate? Well, to do that, I want to take a look at the standard test mixture which you can purchase from many chemical vendors, many of which are at this conference. So I'm looking at this polar iso test mix, which I chose because it has a number of different compounds that have different functionalities and also carbon contents. So we have alcohol, chlorine groups, amines, and some esters here. So we can look at a standard FID signal, and we see on a DB5 or 5% phenyl column, we get separation in this mixture, and we know the order of elution because it's a boiling point column, and we've seen this test done before. So from the chromatogram here, we can get the peak areas, but we don't, of course, know how to relate these peak areas to concentration since this is just a standard FID signal. We need to know the response factors. So what do we all do in this situation? We do calibration curves. 5-point calibration curve. In this case, here I'm taking the response of aniline, or the third component, relative to some internal standard ethanol area per mole of carbon, and I'm looking at the response here. So in this case, this means that aniline has 1.45 times greater response in an FID because the carbon compounds in aniline have a greater response than ethanol. Ethanol has less propensity to form those carbon cations in the flame ionization detector. We also see a non-zero intercept, which indicates that there's some error in this sample, which could be due to when I was actually making it, and there was some vaporization happening when we were adding these different concentrations. We can repeat this for all 9 of the other components. Again, there's one internal standard. And we can create calibration curves for all of these components. Again, an arduous task. And now I can put an unknown sample there with an unknown composition, and I can read off the concentration from these calibration curves, and I can look at what the error was because I'm actually using a known in this case. We're just treating it like an unknown. So if we look at now the error associated with this, it's between 2 and 6% with these 5-point calibration curves. There's a little bit higher error with the earlier eluting compounds, probably because of some of the volatility issues when you're making the samples. So let's contrast this now with using a reactor that converts everything into methane and not doing any calibration at all. So we're going to take the same unknown sample and we're going to run it in our reactor, converting it all to methane before going to the FID, but of course after the separation. And we're going to use this formula, which is just the response factor formula, but with response factors of 1, because again the response per carbon is just 1. So we can calculate now the moles of carbon for each species just from the area of this chromatogram. And what we get in orange is similar, if not better, errors on average than using a 5-point calibration curve with the FID. And again, this was a sample that had a number of different types of functional groups and atoms, and also size of molecules. So we do ship this test device with this test sample with every single Polyarc reactor that we sell. So what is this magical device? What is the Polyarc Reactor, and how does it work? Well, this is the Polyarc Reactor. It's a 3D printed stainless steel reactor, and we 3D print rather than machine it so that we can get the extreme attention to detail that we need to have a complete conversion to methane while still maintaining your chromatographic performance. The reaction happens in 2 stages. First, we combust everything to carbon dioxide and water, and then we reform all that, or methanate all that into methane through a reduction process, and we get larger than 99.9% conversion to methane for everything that we've tried. So where does this fit in a typical GC? Here's a simple schematic of a column that fits between your injector and your FID. We simply insert our reactor between the column and the FID so that you do your separation first, and then you convert everything into methane sequentially as it comes out of that column as it goes into the FID. And sorry, that was a picture of an enclosure for an Agilent GC. It does work with other GCs as well, but this would fit right in one of the detector spots, right on the position between the oven and the top of the GC. So next I want to show you a few examples of compounds that I think will be quite interesting for this particular audience. The first is a mixture of C5 to C18 in alkanes. We've also tested over C30 alkanes as well, and there's no issues there. So pretty much if you can get it through the GC column, we will react it to methane. So this concentrated mixture of C5 to C18 in alkanes, you see the signal. Everything is converted to methane here, and this is the FID signal that we get. We can first look at the response factors that we obtain for each of these alkanes, so C5 through C18. We see they're all about 1 within error. And the error in the concentration determined using the Polyarc reactor with an FID is smaller on average than using the FID alone. If you assume, in this case, we assumed that the response factors were all 1, which we know they're not quite, but many of us assume that for straight chain alkanes. I know I did in grad school. So you're getting better error for those using our reaction to methane. We can also look at a calibration mixture of C1 to C6 in alkanes, gases. And here is, again, is the chromatogram. Everything's converted to methane in this case as well. And we see response factors that are 1 within error for these as well. We have a number of different examples that we could show you, but I don't have a lot of time. Here's just a snippet of some of the molecules that we and some of our customers have tried in this reactor, including silicon derivatives, sulfur-containing compounds, nitriles, halogenated compounds, aromatics, and some nasty stuff in there. And there's been no degradation in performance with our reactor. These represent a set of a lot of molecules in different industries, such as pharmaceuticals, carbohydrates, flavors, fragrances, and food, cosmetics, and chemicals, of course. And of course, petroleum and gas. So we're very proud that we've developed a reactor that lasts a very long time. We've tested over 5,000 injections with a number of different compounds. Here we're looking at the response factor as a function of the number of injections, which is giving us a surrogate for the degradation of the reactor. And we're looking at ethanol N-heptane neat injections, which is really straining the reactor because we're putting a lot in there. And we see no degradation of performance over that lifetime. We're also injecting other things in the intermediate spaces here. We've designed this reactor. We know it's a catalyst-based system, so eventually you will need to replace it. We've designed these to be replaceable cartridges that have all the catalysts in them and have been fully tested at activated research companies, so these can be priced quite a bit lower, and you can replace these every 6 months or so when you start to see degradation. So in conclusion, we find that the catalytic conversion of gas chromatograph effluents to methane is an accurate and a versatile method for improving FID analysis with GC. This technology was developed by Activated Research Company, and it's not available anywhere else. It provides a consistent and robust conversion of molecules of all types. We've also seen that there's negligible impact on separation performance. We see band broadening on the order of 10% due to that reactor being in there. There's a very long lifetime of that catalyst cartridge, and it is replaceable. So we encourage you guys to go to our website and look for more information. I'd be happy to take any questions at this time, but please visit us at our booth as well, and the new product showcase, and vote for us for the best new time-saving device. I appreciate your attention. I'll take any questions at this time.